All right, so in this problem, we have M production centers with respective availabilities A1 to AM needing to be shipped to N different markets with demands denoted B1, B2, all the way up to Bn. We assume that the supply is equal to demand, and we are assuming that the unit transportation cost from the distribution center I to the market J is Cij. Now, we want to develop a linear programming model to identify a least cost shipping plan. So we're trying to make an optimization problem here. We need to create a decision variable corresponding to the amount being shipped from each production center to each market. So we are going to write this out as let xij equal the number being shipped from the production center I to the market J. Now, combined with this cost variable here, we are able to create our objective function. Remember, we are trying to identify a least cost shipping plan, so our problem will be a minimization problem. Start off, minimize. Now we are wanting to go through every combination of production center to market, so we have to do two different sums. So we'll have from I equals 1 to M, this is going through each production center, and then we'll have from J equals 1 to N. This is going through each marketer. So we have the cost times the amount shipped. This is going to be our objective function. So there's only going to be two constraints we have here. We want to make sure that the amount shipped from an arbitrary production center I is never going to exceed the amount available in I. So we can write that as subject to, first off, that from J equals 1 to N, so we are going to be going through each market. Want to make sure that the sum being shipped specifically from production center I is never going to be greater than the amount available there. We're just going to set this as equal, and we're going to say from I equals 1 to all the way to N. Similarly, we want to make sure that, because each market has a specific demand, we want to make sure that the amount being shipped across all of the production centers to a specific market is never going to exceed the demand. It's a very similar constraint. We're going to write down from I equals 1 to M. So across every production center, we want to make sure the amount being shipped to J is going to be Bj from J equals 1 to N. So with these constraints, we make sure that the amount being shipped from a production center never exceeds the supply, and the amount being shipped to a market never exceeds the demand. And because we cannot deal with negative values being shipped, we're going to say that xij equals greater than or equal to 0 for I from 1, 2, all the way up to M, and j equals 1, 2, all the way up to N. So we are done part A. So now we have our linear programming problem. We want to now assume, this is what part B is asking, we're assuming that a non-negative cost Dij is going to be charged for any positive shipment from production center I to market J, and we want to give a new problem to reflect this cost. We have to introduce a binary variable here, so we're going to denote this as Yij to equal 1 if Xij is greater than 0 and 0 otherwise. We do this because Dij only exists if an amount is shipped. So to make this look a little nicer, we're going to introduce some sets. We'll let v1 equal 1 all the way up to m. So this is going to correspond to the production centers. We're going to let v2 equal 1 all the way up to n. This will correspond to the markets. And then we'll let s equal each pair where the cost is positive, strictly greater than 0. If it has 0, we don't need to worry about it. And now our optimization problem will be like this. We'll have a minimize as the objective function again, and we'll have same thing as before. We'll go through each production center and each market, Cij, Xij. However, to incorporate the non-negative cost that is fixed, we will have for each pair in S, so for each pair where the cost is positive, we'll have dij times yij. So this is basically the fixed cost, and we're only, given how we have defined our binary variable, we're only going through the ones where an actual amount is shipped. Because it's fixed, we do not need to multiply it by this value here. So this is our objective function. And then our constraints are going to be very similar. We will have I'll just quickly write out the previously mentioned ones. Subject to j equals 1 to n, xij equals ai for I in v1, which we have defined up here. And similarly, from I equals 1 to m, xij equals bj, j in v2. We can note that yij is in 0 or 1 for ij in S, so the pairs in S. And then we can once again note that xij is going to be greater than or equal to 0 for I in v1, j in v2. Now we are going to introduce a new variable. So we're going to let m equal the minimum of one of these two values, either the maximum value uh, of supply across all of the production centers, or that's supposed to be a 1, or the maximum demand across all of the markets. And we are going to say that the specific amount shipped from production center I to market J can never exceed this value, m times yij. So in other words, we're saying that one specific quantity shipped can never exceed the minimum of either the maximum supply or the maximum demand. And that is the final restriction that we need to have. Therefore, we have formulated here the answer to part B, and we have formulated here the answer to part A. And now we are done.